Okay, then I will start. I feel very nervous to use this mic, and okay, to begin with, we in this class, I uh, I will lect about linear algebra, and it is very elementary linear algebra. So because it is the main purpose is the main purpose is to introduce some concept of linear algebra and the application of linear algebra. And actually, another main purpose is practicing my English skill. And so it might not be a kind class for you, but I will try to do my best to convey the concept of linear algebra. And so I will sometimes give historical concepts. And the linear algebra is developed from 18th century and to earlier 19th century. It is a little modern concept, but before that, there is this linear algebra concept, and actually the determinant is developed more before the 18th century. So the linear algebra is started from the Gauss-Jordan elimination. So in today's lecture, I will introduce what is system of linear equation and how to get the solution of the system of linear equation. So the main chapter is systems of linear equations and the matrix. We will embody to a matrix in the matrix, and of course I will explain what is matrix. I will use the textbook elementary linear algebra of Howard Anton. But I think you do not need to buy this book. I will give my lecture notes and almost things similar, same to the textbook, and I will. This is a little expensive, so you do not need to buy the textbook. I will give some information, some documents. And in this book, the author want to convey the application and very elementary linear concept. So in the first chapter, we will this book starts from most of information in the world, and the information usually can be presented by arrays, and actually usually the rectangular arrays is called the matrix, and it is not definition. I will introduce definition more later. And for example, I will give an example of linear system. One linear equation is 5x plus y equals 3, and another equation is 2x minus y equals 4. And it is multivariables. These are multivariable variables equations. Degree 1 equations of degree 1. So this equation will be called it linear equation, and some linear equations system is called it a system of linear equations. So we will finally we will represent this the form of like this. So this presentation is matrix, and matrix needed just the coefficients of these elements. So almost mathematical information will remain the abstract part, and this equation is also developed from the trading system. So in the world, if you want to get the optimized solution in company, or you want to get more, you want to do the best value, you want to get the best value in trading when you trade. So these some equation from the situation we want to get the solution of the equations, but it is not only unique, and we do not know there is the existence of solution also, and this linear algebra will give some answer of this question: what is solution, and is there the solution something. And so the first chapter is what is linear equation, and what is the let me introduce system of linear equation. So let me give the definition of linear equation. We define a linear equation. In linear equation is needed variables, because we want to make some equation, so we need variable, and by using that we define linear equation in the n variables. X1 to xn to one that can be expressed. In the form a1 x1 a2 x2 plus continuously an xn equal b. It is like this form, and here the a1 to an and b is constant, and in and the variables are called unknowns. And in this sense, it does not. It is important a from a n, not all zeros. Because if they are all zero, then b should be zero to get the solution, and in this case we get just only 0 equals 0 equation, and it is not interesting, not have any meanings. But b equals 0 case is fairly interesting points, because by adding on a variable x0, we can make this similar equation, similar linear equations like this. Let's consider the situation. There is one more variable x0, and b is also constant, so we will denote b. We will denote a0 as minus b. Then this equation will be changed by the following forms. a0 x0 plus a1 x1 an xn equal 0, and if we substitute to x0, substitute x0 to 1, then we will get the equation, the following equation. And this form is called the homogeneous homogeneous linear equation. And I showed how to construct a homogeneous linear equation from a linear equation, and this method sometimes called it homogenization. And this concept is very important in algebraic geometry, and in the linear algebra case, we will see only degree 1 case, So in this case, it might not be important, more important than other algebraic geometry, because we can get the solution more easily. But I want to give some information. The homogeneous polynomial and homogeneous linear equation is important. I wanted to convey this concept. So I will give, let me give example of the linear equation. So I mentioned one thing. We just use only degree 1 case. So the linear equation will be formed like this. And before I explain the complex number, I will give only the coefficient will use only in real number. So these are all the examples of linear equations. And actually, in this case, is homogeneous linear equation, and it can be used like this form also. And then you might think, what is not what example is there? Is there not linear equation case? Is the not linear case, not linear equation case is that x plus 3y square equal, for this case, did not use only linear variable. So in this case, it is not linear equation. And also, as the multivariable, x plus x multiplication y, x multiply y is also has degree 2. So in this case also is not linear equation. And the transcendental function is also cannot be written this form. So it is also not a linear equation, and square root is also not a linear equation. And I want to explain more than this form or this form, because I explained what is homogenization, and homogenization real means making the equation have same degrees. So in this case, by using one more variable, I will use that. Then it can be also homogenized. Not square. xyz equal 5z square. Then all degrees are 2, and this system is homogenization. And but another equation case, we cannot change it to this form or this or this. In this case, we should use z from z or z square, but square root of x1 cannot be. It has. I don't know. We say degree 1/2. I don't know it is right, but in this case we do not say it polynomial because polynomial has only natural numbers degree. So in this case also, okay. That is another variable. Another variable is that. Yeah, I multiplied. I want to make another. I want to make same degrees. So in this polynomial case, the most of the term of most having most degrees are 2 from xy, and in linear case we made a homogeneous linear equation by adding one more variable, and because having same degree. Yeah, for making generation. Group. I think the price rule is explaining the price rule is a little difficult, but simply if I explain, we made in this case we will made degree 2 polynomials for each terms, and we have 4 terms, and this term has only degree 1. This term's degree is 1. So to make degree 2 terms, then we need one more degrees. So the added variable will roll in this equation as the to make same degrees. So in this case, we made xz to make degree 2, and the second term is also by multiply z we made degree 2, and the term having both the most degrees, we although we do not multiply z, we already get the degree 2 terms, and the final term was coefficient, but if we multiply z square, then this term is also will be degree 2 terms, and by substitute 1 instead of z, then this polynomial will be original polynomial. So from this if we get the solution of this, then we can get the solution of this also by adding z equal 1. Yeah, yeah, different. If z equal not 1, example, if z equal z was 2, then this equation not will be equal, but it is not focusing our question because we want to get the common solutions. So in the common solution case, we will give one more equation z equal 1. Thus, we have this. We will get common solution. So we have some equations, and we will input one more equation z equal 1. Then this system solution is same to this system solution. And this system will this system became homogeneous polynomial system, and we have some method to solve this homogeneous polynomial because in this case, if we give multiply for each the variables, like I will use these equations, homogenize this equation, then xz plus 3y square minus 4z square equal 0 case, then if we input x, y, z, instead of 2x, 2y, 2z, then this equation will be 2x, 2y, 2z plus 3, 4 square minus 4z square. And if we use commutativity, then this will have same multiply for each terms, and the homogeneous polynomial, the right side is always 0 because we call homogeneous polynomial having this form. So we canceled this coefficient. So actually, eventually we can get the same equation, the first one. So in the homogeneous polynomial case, we have this good property. So by using this property, sometimes we get the common solutions more easily than just polynomial equation case. Okay, the answer. why use this homogenization and how to construct to homogenize. Yeah. Yeah. I think if you make some just linear equations, and by making homogeneous linear equation from them, then you can get the meaning of homogenization. And actually, in this case, if the all variable, if all variable has 0, then it will have the solution in the at the origin. It is also sometimes give some method to get the solution. And I think it is more difficult concept, and it is not linear concept, and sometimes might use the more advanced concept in algebraic geometry, so I will skip that. And I recommend to make homogenization like this form or this form. Or polynomial can be written can be written this form by using homogenization. Yeah, but it is important, so I will use them. Yeah. No, it kinds of situation, because if we want to original solution of original equation, then we should input one more equation z equal 1 in this case. Then to get original solution. And just if we do not enter this solution, this equation z equal 1, then we will get the homogenized polynomial solution set. But it has also geometrical means, because if I see just the linear case, then the linear case is figured like flatly, like this line or plane, and the common solution will be pointed at intersection points or equation solution like this. Then from this we will find solutions, and how many there are solution, or is there a solution if the line are parallel, then in this case we can see this linear system does not have solution. So in homogeneous linear equation case, it always throw the origin, because 0, 0 is also every homogeneous polynomial has this point as solution. So we can get more geometrical, easy concept of geometrical. And okay, to explain more more, then I think you need algebraical geometry concept, but I will not explain in this section because in the linear algebra we do not need the concept of more geometrical concept. And then we will construct, let me introduce the system of linear equations. It is a finite set of linear equations. This means we do not need just one equation, and the equation, the number of equations has finite number. System of linear equations has finite number of linear equations. Or sometimes, more briefly, we say it linear system, just linear system. And in the first I explained we want to get solution of this equation, so I will define what is solution. And if for a sequence of n numbers, we will substitute to x1 from x1 to xn. So if the sequence s1 to sn make each equations in the linear system a true statement, then that is x1 equal s1, s2 equal s2, sn equal sn makes each equations true. Then the sequence s1 to sn, the finite sequence is called the solution of our linear system. Linear system. And I think we define from sequence, but it use only finite number of. We use only finite number, so usually we denote S1 to Sn like this, and this form is called n-tuple, ordered n-tuple. sometimes n, when n equal 2 or 3 case, we sometimes state it order the pair or and respectively. When n equals 3 case, we sometimes called it order the triple. I think usually we use just n tuple or order the n tuple. Can I turn off the heater? And in general, we say the linear system is consistent if the linear system has more than one solutions. There's at least one solution. And inconsistent if the linear system is inconsistent if it has no any solutions. The homogeneous polynomial in this statement, from this statement, we can know that homogeneous polynomial is always consistent linear system because the origin will be solution from of the homogeneous polynomial. I will let me give one more remark. We, as I explained like this, in the linear system will be written, will be drawn by line or plane because it has only degree 1 polynomials. It is used only degree 1 polynomials, and from that we only get like x equal what, y equal what, not x square. Do not use have this curved this curve. We only use just line from the linear equation. So in this sense, we can see the fact every every system of linear equation has 0 or 0, 1 or infinitely many solutions. Like if we see some graph, I will use line or plane as to explain this. if the line is parallel or in R3 planes, R3 space, then there are briefly there are three cases. One is like this line. This is two line, and it is on R3, and so it does not intersect in any point. And it also will say parallel because we do not meet. So parallel case. And there is another case, intersects just one point. And two lines have same. If the line was same, then we get infinitely many solutions. And actually, in the plane case, also has similar solution, because in the parallel case, plane also has in the parallel case, it has no solution, and intersection case, the plane will intersect in the line, and if the plane was same, then it will intersect on plane, and in these two cases has infinitely many solutions. So expand this concept, and we can get this statement: every solution, every linear system has zero solution or one solution or infinitely many solutions. There is no any other cases. Let me give one more definition. Parameter. About parameter. We made this solution. We defined the solution. What is solution? But the solution, if we collect all solutions, then it can have infinitely many solutions. Then if we do write all solutions each other, then it will not be fine. Will not be fine. Finished. Will not be finished. Yeah, counting it is impossible. So we usually write it by using parameter, and the parameter is, so it is used to describe the solution set. We assign an arbitrary value like t or s or something, and which is called it parameter. And we will substitute 2 on variable. Variable. I will denote unknown. Unknown is x1 or x down to xn. For example, to solve this linear system, in this system case, we can get the solution by substitute from first equation to second equation. Then we get minus y, or is it right? Oh, just like yeah, okay. Y for is there, I'm not good at calculating. Okay, let me check. From this we can get 2x equal 6 and yep, by substitute y equal 4 to this equation, then we will get 2x equal 6, and if we substitute this, then 6 is wrong. I think it is right. Minus y. This equation minus this equation, then minus y equal 4. Okay. Y equal minus 4. Then it has only one solutions case. Y equal minus 4 and x equal 3. I'm not sure. X equal minus 1. Y equal 4, then 2x plus 4 equal 2, then minus 1. Okay, thank you. In this case, this solution has only one solution, but if we consider the equation, linear system of linear equation, then if we multiply 3 on the first equation and if subtract to second equation, then we will get 2x minus y equal to 0 equal 0. So in this case, we get y equal to x plus 2, and if we find the solution set, then it will be drawn this line to this line, and to write it as a solution set, then we assign an arbitrary value t to x, then y became to write this. So the solution set is two tuple t comma 2t plus 2, and t is in real number. We will we will write like this form by using parameter, and it is role of parameter. So these unknowns is not considered in the linear system because it will have n unknowns always if from the linear system get it has from linear system, then it will finite number of equations and finite number of variables. So to denote more simply, we use matrix, the matrix form, and let's consider the indeterminate linear system. A1 x1, A11 x1, A12 x2. All linear system will written like that. AM2 x2 AMN xn equal bm. Then we, by abbreviating the x1 to xn, we reduce this like this form. B1, B2, BM, AMN, and this matrix is called augmented matrix. It is a kind of matrix, and it is gained through system of linear equations. And by using appropriate operation of matrix, then we might have the solution of linear equation. And today's main purpose is to explain the method to find the solution, the common solutions. Before we begin, I explained about Gauss-Jordan elimination, and it is origin of linear algebra to find the solution of linear system. And to explain this method, we will define one thing. It is reduced row echelon form. It should satisfied for statement. And the first property is related to leading one, and if a row does not consist entirely of zero, then the first non-zero will be called a leading one. We will make this form finally, so I will explain what is reducible echelon form. We call this leading one. And the second property is the same. If there are any rows the consistence entry are entirely of zero, then I will write first. If there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. So this means we will change the row if there is 0, 0, 0 rows, then it will be go to bottom. And the third property is the leading one in the lower row course further to the right. To the right, then the leading one in the height rows. This means if there was two leading ones, two more leading ones, then as a second condition, the zero equation will go to bottom, and if there were two leading ones, then if the higher one is in the more left side, the third property says this, and finally if we have leading one, then in the below side all zero. As zeros. Everywhere else in the column. And upper side is also. So I will give example of this echelon form. The augmented matrix, it became like this, then this form satisfied these four properties. If we see the row with row leading one, then the column has only zero, and another leading ones is there is more left side, and another leading one column has zero. So this form, this is also reduced row echelon form, and more generally, if I give another example, then 1 0 0 0 0, and there is some number. This matrix is also satisfy these four property, so this form is also reduced row echelon form. And if we check that, then the four property said this leading one's column has only zero except leading one, and in the first property said the left side all zero, and the second property said all zero rows will go to bottom, and the third property said for higher reading ones is position to the left side. So if it although it is not zero, this star is not zero, it will be reduced echelon form. And by making this form from our system of linear equation, then this term is the right side of equations, and this term will be variable unknowns, and we can get correspond to linear system. Then 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, and B. Then X, if I written this line, then X9 equals star, and X7, 9, 8, 7, 6, X6 plus star equal star. Then by inputting parameter, we can get the solutions. We can construct solution set more easily by using this form. So we define this reduced row echelon form. So I explained if we accept proper operation of matrix, then we might make this row echelon form, and from this we will get the solution set by using Gauss elimination. So let me give one example. I said one remark, and the remark number was 1.2.3. I will make small augmented matrix directory. If we have this linear system, then this linear system, this matrix is an augmented matrix. So this means if we assign variable, then 3x1 plus 4x2 plus 2x3 equal b, not b, 1, and 2x1, 4x2 plus 2x3 equal 2, and finally 3x2, 3x3 equal 6. So to find the solution, we calculate by adding or subtracting each equations. So we will use this rule as the matrix. Then I will change the number. Because it more to calculate more easily. And if we subtract from first equation to second equation, then we get 0, 0, 0, minus 1, no, and 0. We will divide. Wait, okay. We will divide 3 in the third equation, and to make reduced row echelon form, we have only leading ones in the most left side, so we will make number 1 by dividing 2. And in the leading one, over the leading one, we have only left side more higher row or higher row, but in this case, if we divide minus 1 in the second row, then the echelon form, it cannot be echelon form by second and third equations, so we will change these two equations because if we see this equation samely, 3x2 plus 3x3 equals 6. These three equation system, these two linear systems is same, so I can change the order. So it can be written like this. And by using third equation, we reduced these terms. I think and by using this second equation, we also reduced this first equation, and then we made like this form. The last one is by using the last row, we multiply 2 and subtract second line, and multiply 1 over 2 and subtract to the first equation. And also from that, then we can get the second row, and by subtracting 2 second row, the second row subtract 2 the first row, then we can get this augmented matrix. And this form is reduced echelon form. Reduced the low echelon form because the leading ones column there is no another number except 0, and the leading rows the right side equal all 0, and we check the board property, the first property, and first property, and the third property said it placed left side, and there is no all 0 equation, so we do not check. We do not need to check the second property. And finally, we correspond to the linear system for this augmented matrix. Then we get x1 minus x3 equal 0, x2 plus x3 equal also 0, and 0 equal minus 1. It does not have solution, but by using this equation we might have the solution set. In this case, the final row was 0, 0, 0, 1, so this equation means 0x1, 0x2, 0x3 equal minus 1, but we say the linear equations do not have all coefficients is 0 or 0, so actually it is not linear equation, it is just wrong equation. So we can know this linear system does not have solution. And if I change the little remain this from this. If we change the second term to 1, then this term is 0, and we will replace it to the final line, and then the equation will like this. So finally, the echelon row, reduced row echelon form will be 1, 0, minus 2, minus 1, minus 4, 1, 2, 0, 0, 0, 0. And if we correspond to linear system, then we get x1 minus x3 equal minus 7 over 2, x2 plus x3 equal 2, and binary equation does not have any special means. It is just correct statement. So by assigning a parameter to x3, then we get the solution sets plus t 2 equal 2 minus t and x3 equal t. We get these solution sets. So the reduced row echelon form gives infinite solution, and also it the answer of existence of solutions, and we can get that means we can get the solution sets more easily. And by assigning the value to parameter, then we say that it the general solution of the linear system. I explained this algorithm and to make reduced row echelon form, and this method will be divided two parts in the historically. By making this form until this form is called it Gauss elimination, and if we find the final form, then this all method will say the Gauss-Jordan elimination. So until if we made augmented matrix by using Gauss elimination, then this form is just row echelon form, not reduced. This form was called it reduced row echelon form, and this form will be called it just row echelon form. And I bring another example, and if you want to get more exercise, then I will give an exercise problem. By using Gauss-Jordan elimination, you can find the solution set of this linear system. It might be a little big, but I think you can get the solution, and its calculation is not difficult. Yeah, by using augmented matrix, you might solve more simply. Just solving this equation from this equation. I have solved this, but its number is not difficult. Maybe you can also get the solution. So I will give an exercise. If you want more exercise, then try it. And I explained about just linear system, and the beginning I explained one more system, homogeneous linear system, and so briefly I will explain. We do not explain system of homogeneous linear system. We just explain homogeneous linear equation. So in this sense, homogeneous linear system is also similar to linear system. It is also a finite set of homogeneous polynomial. Not polynomial, linear equations. Is called it homogeneous linear system. So homogeneous linear equation is also linear equation, so we can use this Gauss-Jordan elimination or Gauss elimination. So from using this method, we can get the solution set also. And I explained the homogeneous equation has always at least one solution, because the origin is always the solution of homogeneous linear equation. So the origin is called the trivial solution, and another solution is called the non-trivial solutions. I will give two theorem, and it is not difficult. So after I introduce this theorem, we will get rest time a little. I think it is necessary. The first theorem is about homogeneous linear system, and if a homogeneous linear system has n unknowns, and if the reduced form echelon form. Okay. Has R non-zero rows, then the system will have n minus r free variable. We will call it the number of the parameters using parameter unknowns. We will say this term is free variable. So then the system has n minus r free variables. And it is not difficult to prove, and I think it might not be called proof. Let's consider the situation. We have n variable, and it is homogeneous polynomial. So the most right side is all 0, and if we consider the situation are non-zero row, and then we no. Another one is all 0. We assume this situation, and from this situation we will get R leading ones. We don't know where it is, but it will be more left side for each higher rows. So this will be formed like this, and then we will make the corresponding equations f I1, fi2, fir. If we give the index like this, then xi1 plus blah 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 is 0, and xi2 plus blah blah is equal 0. Finally, xir plus what is 0, and we will give another parts as a parameter, and then we have R unknowns. It will be called leading one. The variable as leading one is called leading variable. So we have R leading variable. And there are another n minus r free variables, except these leading variables. Oh, not leading. Free variables means if we give parameters to the free variables, then we can get the solution set. We can express the solution set by using the parameters. 2시까지는 쓸 것 같은데. And another theorem is a homogeneous linear system with more unknowns than equations. Then it will has infinitely many solutions. Because from the above theorem, if we have free variable in this assumption means there is there is free variables because we these equations if there are equations and there are more than there are n variables more than r equations, then there remain n minus r free variables, and this means the linear system will have more will have infinitely many solutions because we should use parameter, and parameter will come from real number, all real number. Okay, let's take rest time. Okay, then I explained how to make the reduce the row echelon form, and so in the computer case, by using Gauss-Jordan elimination is not usable, not more usable than just Gauss elimination, because the another step is only for searching by hand. That by making reduced row echelon form, we can get strict solutions by using parameter. But in the computer case, just inputting parameter to the free variable, we can get the solution. So to apply to computer, we usually only use Gaussian elimination. This book explain these computer science concepts. Sometimes deal with this subject. I don't know. Okay, remark. Oh, I delete the title. From the row echelon form or reduced row echelon form, there are some facts that first is every matrix has a unique reduced echelon form. Because when we made reduced echelon form, we made like this form. And this form means this variable, give this variable as the another free variables, and this column vectors means the kind of variables. So if the solution is not changed, then the final echelon form, the final reduced echelon form will be same, because this form is saying the solution set, and the solution set does not change it by calculating matrix row calculation rules. So the reduced echelon form will be unique. But just row echelon form by using Gauss elimination are not unique. Obviously, by changing the row, we might get another row echelon form, just row echelon form. Then it can be changed, because we do not use the Gauss-Jordan elimination, so it will not be reduced to the solution set, and this means the row echelon forms might have some wait, and I will give one example. If the augmented matrix is 1, 2, 2, just simple example. 2, 1, 1, 0, 2, 2, 2. I'm not sure it will give another solution. Yeah. So if we change the row echelon form might be have another solution, another form, another matrix. But finally, we use Gauss-Jordan elimination, then it will give unique solution as the solution set. And third one is reduced echelon row echelon form gives some information of the leading ones. The same number of zero rows. This means we will, if we take the second property of reduced row echelon form, then we will move the zero row to bottom, and the number of zero rows is same to reduced row form and all row echelon form. And the leading one always occur in the same position. Because we the parameter variables and free variables and leading variables is this means the free variable and leading variables are defined from original matrix. So right. To be specific, I will explain more about three. If we use this row echelon form, just use Gauss elimination. And the reduced row echelon form is used Gauss-Jordan elimination. And Jordan parts, the later parts, is only calculate, remove the upper rows, the higher rows on the leading ones, like this. Oh, 0, 1. We calculate just these parts in the Gauss-Jordan, the later parts, the second part. So it does not change the leading one's position. So they occur in same position. Then it has special mean. So we will define this position. We call this position as pivot. So let me give the definition for the matrix A. Until now, we only use augmented matrix. This is from system of linear equation. The leading ones are coordinated pivot positions, it is well defined because row echelon form and reduced row echelon form, all row echelon form has same position, so it has just one position. It is well defined, so it is well defined. Okay. And the position will be called it pivot position, and the column having leading ones are called it pivot columns. Similarly, the rows having leading ones are called it pivot rows of A. And we will say this entry, this position is pivot points, and this value of entry will be called it just pivot. So I will give an example. If we have an augmented matrix like this, then it by using Gauss elimination, we might have a one row echelon form like this. When you calculate it, you might have another Gauss another row echelon form, because it has it is not unique. It is row echelon form is not unique, so you might have another form, but I will use this form. I will use this result. And in this form, this position is pivot position, and this it was from this, and maybe in my memory it was these three things, maybe. This position from the original is from the original matrix, these positions, and so these values is pivot, and this column is the pivot column, and in this case all rows are pivot rows, because all rows have pivot position, leading ones. So we usually say the leading ones. We usually say this position as pivot instead of leading ones. And finally, I will introduce matrix a little for in order to start easier when we start next class. Then we calculate matrix appropriately, maybe, and we just see the augmented matrix case, but in the real world we can change the matrix. We can present matrix more many things, and then we might need more general operations like addition, subtraction, or multiplication. So I will explain about that. So I explained matrix is rectangular arrays. So in the definition of matrix, is a rectangular array of numbers so we always denote like this, but if I give not matrix arrays, then there is like this matrix 1 1 2 1 1 1 0. In this case it is not rectangular, so it is not called in the matrix. We only call matrix like this rectangular form. It is not it is always square case, because we will call this form as a matrix also. And the number of the numbers in the array, each numbers are coded entry or entries. Plural of entry of the matrix. And it is rectangular, so give the number of rows and columns, then we by giving this information, the number of rows and columns, we can get the size of the matrix. And the size of a matrix is described in terms of the number of rows and columns. So usually if there are m rows and n columns, then we will say m times n matrix or m by n matrix. And also in a special case, we might be able to think there is only one rows or only one columns. Then in this case we will say use vector. If there is one rows, then will be called it row vectors, and if there is only one column, then it will be called it column vectors. So before we start this section, I explained we might need proper operators and to check it is polynomial on matrix, then we might need equal what is same matrix. So to calculate matrix properly, then we should focus the size of matrix. It is very important information with matrix, so it is needed. Thus, I will let me give the definition equal. And it is similar to its system is similar to real system, real number system. And there is two matrices, and two matrices are defined to be equal. If the matrix they have same size and the entries corresponding same position. Are all same, then we will two matrices are equal, and we can I forgot the word. I forgot English word. There is two different matrix, and I want to from this equal, we can compare two matrices, and then if they're equal or not. Yeah, we might give the smaller in matrix, but it is a little different concept. The smaller, we all, in the matrix we, same rows. Yeah, they equal. We until now we cannot compare it. However, by assigning the order to matrix, then we might have smaller and bigger and or equal. it's also comparing, and but in this section I want to just what is equal or not equal. And when we give equality, we might have equation on matrix. The equation sometimes means arithmetic subjects. Okay, 지금